All right, so I'm going to be writing a cache-link prefetcher profiler, kind of. I'm going to explain what that means in a second, but basically, the the different levels of processor caches, data caches, uh, they have almost all of them nowadays a prefetcher, which guesses which lines based on your access pattern which cache lines you might need in the future, and it would prefetch it ahead of time so that once you actually initiate that access request, um, it could already be in the cache, so that you get to cache it and retrieve data with like 10 to 50 cycles, 60 cycles, depending on the cache level. Versus 250 to 400 cycles when it comes from DRAM, right? Depending on NUMA node and stuff. So now the thing is, okay, but like, what about it? The thing is, we don't know how. Like, there is no concrete explanation on how these cache line prefetchers work or what their limitations are, and I think some of the information is pretty aged. Like, for example, the operating system works in 4 kilobyte or 2 megabyte or 1 gigabyte chunks with memory, depending on the page size. That the 4 kilobyte thing is like a base page. You have like 2 megabyte pages are called large or huge pages. You have like 1 gigabyte, but most common huge pages are like 2 megabyte. So, excuse me. Now, the question becomes, since one process obviously cannot access data from another process's pages, will these cache lines be fetched outside the boundary of your 4 kilobyte page? It seems the answer is yes, because there's like many many papers that have attacks that exploit this behavior, where the prefetcher actually just brings in lines into the cache that you don't own. So I would imagine that's a yes. But what could be interesting is to see how many lines does it bring, and whether we can use that in our advantage to the thing is, I'm very bad with words right now, because like I have to not say much to kind of leak the idea behind why I'm even looking at this problem in the larger context of the paper I'm working in, because my advisor would beat me. No, I'm kidding. He's very chill, but yeah. Anyway, we're just gonna be playing around with the cache line prefetcher, see whether it does on different process Intel. I'm gonna be writing the program on Intel because that's the machine I have access to, and later on I'm gonna be testing it on AMD machines. I asked my professor. He said I can just spin up a Zen machine and do some tests, but I'm gonna write it on the Intel machine we have access to. So here, for example, you can see this guy says, okay, blah blah blah. Intel processors, the L2 hardware prefetcher quits when they hit the 4 kilobyte page boundary. So this is pretty much saying, Intel does not prefetch past 4 kilobyte page boundaries. But there are also like next page prefetchers. Now, I'm actually not sure if the next page prefetcher brings in cache lines as well as, like, does it only trigger the TLB entry to be cached in case you need to actually later on retrieve the data, you don't get a TLP miss spike, or it also brings in a cache line from that page. I'm not sure about that, but I know next page prefetchers exist, and NPP attacks are actually, like this paper over here is an NPP attack. Is it next page? Is this guy next page? This guy. Yeah, there is next page, like prefetchers, this and that. Anyway, there are pages regarding that. But here you can see John D. McAlpin, by the way, he's like the GOAT. He used to be a professor at UT Austin. He recently retired. And he's like, he resolves 80% of the questions on Intel community forums. Like, he probably spent months of research when I was working on my paper, just because he had answers to things that are like super niche questions I had. And yeah, I mean, big ups this guy. And he's like, okay, AMD appears to, however, include the page size information when passed to the hardware prefetcher, so that if the page size is larger than 4 kilobytes, you could safely go ahead and prefetch lines up until you hit the 2 megabyte page boundary, when it's not a base page, right? And this makes sense. I mean, to me, it looks feasible. I already showed the paper. They've done it. I hope industry has adopted it, because it's in my favor, and that's what I'm trying to figure out. But there is no concrete answer. So we're going to start. I'm going to SSH to this machine. Okay, there is, I already made a cringe name for the product. Peek Pref. Prefetcher. Pref. Easier to say. And you peek into the behavior of this, prefetcher. Let me... Full size, bro. So I'm gonna actually go ahead and copy a whole bunch of stuff from another project I worked on. Or should I just write it in there? I actually don't know. Anyway, what I could do actually is copy this guy's repo. What do you call it? Let's say this is the RCXB. Yes, it'll see feasible. I'm gonna go ahead and just like clone his repo again, and I'm gonna clean up his repo. I'm just gonna make one single file. Or do I just legit make a single C file? I think that's the best thing. Just do a let's just make a simple C project. So let's do all and C to show that with I've seen people use like -01 when it comes to very fragile microarchitectural code bases, but I've tried with O2. Nothing bad really happens. Nothing bad really happens anyway. I'm gonna call it PP, right? Peak. Okay, that's kind of weird. PKP, Peak Prefetcher. Right. Yeah, I like the name PKP. Right, it's fine. And I'm just gonna put bro here and clean. Okay, now let's do pkp.c and just bring what we need, right? So I'm gonna need this guy. I'm gonna need sysmn. What else are we gonna need? I'm gonna need is it no, I don't need this. I think this is pretty much what I need, right? For now, yeah. Oh, actually, I'm gonna copy this from him. This code base is like a gem. Right, let's search for some files here. Those types, I think it was under include or num types, yeah. So actually I need this one. And custom types, and I'm gonna need all of this pretty much. I'm not gonna use a bunch, but anyway. Then what else do we need? Do we need anything else? Bool. Oh, actually, we probably need a city bool. Okay. Oh, you're crazy. I32 for main, not int main. Yes. I'm a big fan of i32, U32, 64, blah blah blah, this and that. I'm gonna also copy memset, I think he calls it. No. Okay, I actually have his. 1 second. Let me just make a, oh man. Okay, now we can just tmux. We have our PKP session. Do we have one for LC feasible? We don't. I'm gonna go in LC feasible and make a just Vim here. And now in the PKP guy, we can just now open yes. And over here we can just make, let's see. Hello. Make and PKP, please. Okay, perfect. Now, what else do we need? We need from here, I can close this now. What do I need from his repo? I need timer start. I need to do timing. So, yeah, I actually don't need to do all this, right? I'm just gonna define timer start. Like, yeah, let's have the ASM section. Heck, bro. Yeah, the ASM section. I'm gonna. Interesting, didn't copy here, so I gotta redo this. What is happening? Why is bro not copying today? Oh man, I'm cooked. Ooh, why are you not copying? What happened to my lawyer, dog? Okay, I gotta do it the old way. Actually, can we just do timer start and take bro? I mean, why do you do this to me, man? Okay, you know what? Okay, we can do TS. We can do TS, and we do the same thing with timer stop, and we do timer stop. Google, and I guess same as our brother here. We leave the. Oh man, this is gonna be painful if I can't copy. Why? Oh, I could copy. Oh, wait, I already copied this. Don't worry about this. No, I can't copy. What is going on? Why? Why are you doing this to me? What happened to my lawyer, dog? Anyway. So, some assembly here. And we're gonna have our definition for... We're gonna have m-axis. I wanna time the... Okay, time m-axis is an important one. I wanna be able to time in cycles how long it takes to access a certain cache line. So I'm gonna need this. I actually don't need it to be this sophisticated. That's like a very well sophisticated. Anyway. And oh man, I actually can't. Are you being serious right now? How about this? What about here? How about this m-axis? That thing might be cooked. So can we copy here? Please, 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 please. I beg, I beg, I beg, I beg. I beg, I beg, I beg, bro. I beg, bro. I beg, bro. I beg, bro. Please work, bro. Please work. Yes. Okay. So we can have this guy. Then I'm gonna need. Am I gonna need M, right? I don't think so. Am I gonna need this? I don't think so. I don't need any. Oh, I need this guy. But I'm pretty sure this is a less sophisticated version. It's like a worse version of. Oh, I think he has this definition. If we're always in line, we could just do it ourselves, though. Okay, we don't need this thing anyway. We can do hashtag define always in line. We could do in line and always in line. Okay. Now for always in line is defined. This guy. Oh, we could seal flush. Should we replace with seal flush opt? This one could use more CPU pipelines, so that's a goodie. And what else do we need here? Elephants. Oh yeah, we need this guy. We need. I'm gonna grab this guy too, honestly. Yeah, and as you may have thought, this is actually not like this is pretty much what programming before AI was. I mean, I like kind of knowing who has what and just like grabbing pieces you need and just like glue it together. And that's what I like it, like kind of sometimes just doing things a little bit. I don't think I'm gonna need floats or doubles, am I? I don't know, but I'm definitely not gonna need I8s. I'm definitely not gonna need. I'm gonna need anyway. So what else? So this is how I'm gonna do it actually. Before we even write this guy, I'm gonna just explain what I have in mind. I'm thinking if we have like a 4 kilobyte page. If we access somewhere like here, right, and we train, the thing is these prefetchers kind of like get trained on your access pattern. So if you're accessing at a stride, meaning like at a set. Okay, if you're accessing numbers like 2, 4, 6, 8, your stride is 2, right? Similar here. So if you're accessing like here, and then here, and then here, the processor could kind of guess your next access is going to be here. So it would like fetch whatever cache line is in that part of the page, and it would, by simply accessing it, it will end up bringing it into the CPU cache. Now the CPU cache is laid out in like a grid style. You have sets and you have lines, and they work in 64-byte chunks. So they would bring 64-byte from your page into the cache. So now the idea is, what if this is a 2 megabyte, right, page? And of course it's not to scale, but you get the idea. So what I understand is Intel processors, at least, even if it's a 2 megabyte page, they will not prefetch stuff past the 4 kilobyte page boundary, even if you own that entire 2 megabyte region. But it seems, and I'm praying that that is not the case with Intel. So, sorry, AMD. But there's no like solid indication. And I'm looking for that answer on a very specific version of AMD processors. So we got to put it to test. And I think what we could do is we just simply have a program that does access, like predictable accesses, just statically set by me, and go ahead and allocate a 2 megabyte huge page and try and access in a predictable pattern, and hopefully train the hardware prefetcher so that you can know what line to fetch next, and see if it will fetch cache lines after the 4 kilobyte boundary. And the way you could tell whether it did or not is timing how long it took you to access that line after the 4 kilobyte boundary. If the access latency is low, you could have an indicator that you got a cache hit, meaning you got that line back in, you know, something significantly lower than like 200 cycles or 300 cycles, which is a typical access latency for DRAM, at least on the machine I'm working with. That's like the feel I have for it. 250-ish, 300-ish, that's the rate. So you could kind of tell, and I'm imagining this is not the case, but there is this thing with next page prefetchers that we talked about. I don't really know how that's going to be messing it up, there's a lot of questions like I'm gonna write them down, like next page prefetcher. Will that end up pulling in lines from the next page, or does it only warm up the TLB, right? And I do have some measurements on how the TLB looks like when you have a cache line miss, but a TLB hit. So we could kind of test that, which would be cool, right? And on the other hand, how many lines does the prefetcher fetch? Right, that's a logical question. That way, if we know, how can we test that? Okay, how can we even test that? One way is to like, not to only access the next possible line, but like, for example, like 4 lines. This is 4 lines in advance, and see if that one's already fetched, right? Because if you're like training your access pattern to be like this, it might predict that you're gonna take this one, and then this one, and then this one, and then this one, right? But what if you don't access here? You just access like here. You know, like how many lines in advance could it possibly guess that you're gonna need, so that it would bring all of them? So I guess if we find like this threshold wherever this last thing that it will like bring in is, we would kind of have an idea of where how many lines. Maybe it's not a set line. Maybe it's like dynamic. Maybe it's trained to bring in as many enough lines. I don't know. There's just so many questions, but seems that we're gonna get some good results. We're gonna get some interesting results. So let's see. So what do we have here? That's some background. Now, L fence, M fence, these are memory fences. So when you have a very like low level instruction, where you want to load like a very specific 64 bytes of data, and you want to time that, there's many fancy optimizations that modern processors do. They reorder your instructions, so like they would do something before another, when even if you did not write your program to do A before B, if A is independent of B, the CPU processor doesn't necessarily need to wait on B to complete to do A after, or otherwise, right? If something is waiting on something else, and the instructions after that progress are relevant to the state of the ones prior to it, you could run them in parallel, right? So if you don't need to open like if you have two doors and you need to push a button in order to open both doors, and the buttons work in parallel, you don't need to push the door on the first door and wait for it to completely open in order to push the second door, right? Your goal is to just like open as many doors as possible. You just push them at the same time. They do separate things. So same thing with the processor. If they're like independent sections of the code, you can do them in parallel, so things might get messed up. So for example, if you're trying to read how many cycles it took, and you're waiting for a memory operation to complete to the compiler or to the processor, both of them might do optimizations at different nasty levels, but they might look at it and be like, okay, reading the timestamp counter, which tells you how many cycles have passed, is irrelevant to waiting for this memory operation to complete. So I could just read the memory timestamp now and tell it how long it passed before this memory operation completes. So you would need a fence so that it says, okay, no, you got to wait for this memory operation to complete before I read the timestamp, because that's the whole purpose of the timestamp. I wanted to see how long it took the timestamp, how long a timestamp ticked for this operation to complete before we time things, right? So that's where fences come from. Like L fence is a load fence, meaning memory load operations. The CPU pipeline waits until all memory load operations are complete. M fence is a mix of both load and store. And there's like also S fence, which is basically the same as L fence, except it's like it's the same like a memory fence, but it's for stored memory. Storing memory up. Oh my god. Yeah. So, what else do we need? This, I don't even think we need this, to be honest with you. There's a more sophisticated way to read the RDTSC thing. So, oh, we gotta do this guy. Timer start Google and that. Timer start. Okay. Do I do this right? I'm gonna do it right here, you know, for the love of the game. So timer starts Google. And we timer stop Google. So, oh my god, why am I doing this today? And timer, yes, timer stop Google. Should be about good. So, the good thing about these timer instructions is that you don't need to worry about adding the offenses yourself. They already kind of have like it. I remember there was like a big fat comment about in the link above this Google thingy about why they think having certain fences before reading the timestamp counter is a good idea or a bad idea or whatever. I would probably need a timer warm up too, because I remember exactly a problem that took a couple weeks to realize that the issue was just instability reading the timestamp counter, and you sometimes need to just read it a couple of times like a dummy counter, dummy read, just so that it warms up and it's, I guess, clock speed is stable or something, and after warming it up you actually read the results you want. So I'm gonna do that. Timer warm up. To my experience, that Coke is killing me. Can Coke sponsor me? I don't want to be sponsored, just gift me, you know. I'm an international student. I can make money off of any of these, so I just better be gifted stuff from Coke. Anyway, where's his thing? Timer warm up. Actually, I might put bro. Do I put bro here or there? Do we need to return anything for this? Like, I would not, honestly. I remember I used to just do some dummy RGSC reads and that would suffice. So I would not return anything for this. I would just do like, I don't know. Oh. Function cannot return qualified void type volatile void. Interesting. Okay. But can I just, read? I guess you have to return it, just do something with it, and then later on I could just store it in a volatile variable, so that doesn't get optimized away by the compiler if I don't do anything with it. Or there's an unused though. GCC do not optimize unused results from a function. What? I see. No, you wait, volatile. Okay. I'll just return this and just store it in a volatile variable or something, as it was. But anyway, we don't need it twice. We could just return it once. We could just simply return whatever this value is and just Google. Yeah, we could just do this, to be honest. One is enough, based on what I remember. And what else do we have? This guy, nice. I think we pretty much have anything. Now let's just do mmap shared init private or something. Okay, I love this code base. It has everything. So this one will just mmap us a single page. That's gonna come in handy. Oh, also I need maccess. Did I get maccess? Yeah, I did. Well, I might tweak. I'm literally on the function itself. Mwrite we don't need, but memset. I remember he used to memset a bunch of stuff. Yeah, but the mset was a part of a larger function. Oh yeah. Okay, so it was the same file, same function. All right, so mset. Oh, this is a function that goes down here. Mmap shared. What is mmap shared then? Mmap shared. Oh, shared. Heck no. Mmap private. Yeah, I want a private file, not a private page, not to be shared. I like my pages private. I like my pages private. Okay, what do we have? We have mmap project. We need to grab mmap itself. Oh my god, what happened to me? Look, electrocuted. Okay. Anyway, memset is fine. Mmap private is fine. Gotta go before this guy. And mmap private static always run this and that. Yes, handles the null itself. Memset. Where does this guy come from? I thought it's in sysmn. Oh. No, memset is string? Yeah. It should be. Oh my god, what am I doing? Why am I importing it here? Okay. Alright, we don't need this guy also for the purposes of this. Okay, and let's just format TS and format TS. All right, then what else? What else is left? Nothing, right? Every time I say nothing. Oh man, I'm a huge. I want a huge page. I'm a huge private, please, and init. We basically need this and just 14 lines down. All right. We don't need this guy. We don't need this guy. We do need that guy. We don't need it. Okay, that line, and then. All right. This looks good to me. Now we could start. For the love of the game, just make sure I didn't. Holy, what am I doing? Okay, just as you know. Oh, by the way, I think that 01. I don't need 01. I need we could just do 02. Should be fine. Right. What else? What else? Let's start by testing. Okay, first of all, I can just start by writing by having a base page, right? mmap private init. So what you want to init with, void address. I think he passes in like a or something. Mmap private init, right? He passes like. Okay, I'm gonna pass in like, I think you could pass in anything, right? Any initialization value. A U8, so you could a character, so you could do like a or something, you know. All right, null, and then I'm gonna do one page for now. For now, I'm gonna just do one page, and oh, actually, I might need a bunch of other page size and this guy. I think this is gonna be this, and this is gonna be, if I'm not wrong, this is 4 kilobyte and this is 2 megabytes. Yeah, so it should be fine. Yep. Okay, yeah. Huge page. Base page. 4K. Now, what I need here, I should probably just respect the guy and just put this here. Okay. Yeah, looks good, looks good, looks good, looks good, looks good, looks good. All right, now let's do a page size. And for this guy, just do like 8. Now, I'm gonna show you guys how you could timer start and actually what does it return? The timer start go 64. Okay. It doesn't warm up, so I gotta do timer warm up. Timer warm up. What was this guy suggesting? You store things in. Okay, I'm gonna do no. Okay, I'm gonna do like a U64 volatile pointer or something. Volatile. Yeah, I don't need this though. Volatile. Warm up, just W, and then timer warm up. What happened to my timer warm up? Warm up? Oh, it has like a, that's why it doesn't show up. Timer warm up. And memory stores a low percentage of the memory access has side effects and therefore must be preserved. Okay, that's good. Yeah, should be enough then. And also, there is a compiler barrier. I think compiler barrier, yeah, it's like a barrier of some sort. Yeah. So I'm just gonna, this is not even worth like making a function for, it's like one line. Okay, what else? So we have a base page and we already have this guy, and if we m-access, right, the guy, what happened? Right. M-access, I think he has like an underscore or something for it, so I should probably remove it. So m-access the guy does, and yeah, and then you do use this. You basically just like copy this and paste it down here, and T2 timer stop. right? So I think it should be LD or something. It took whatever this is, right? So then T2 minus T1. Now if we run this, it took 28 cycles. And that makes sense because when we initialize it, we write to it, right? And once you write to it, you warm it up in the cache. So it's already in the cache. And barely anything happens here. Like there's no memory critical operation that evicts anything from the cache, and this probably all runs in like a couple cycles. What is the... I think I could just show you actually. Let me go to that make file. What is it actually? Was it dash? I think it was like dash S, and then something like pkp.asm, and then pkp.c. I can give it a try. I'm not sure really. Yeah. Okay. This is right. So where's the RDTSC? So yeah, line 60, line 67. Okay. Sorry. Let's go back to this file. So 67 is here. Yeah, so not this one. We need the one happening at timer warm up. So warm up. Basically, the volatile was down there. It's gonna be towards the bottom. Yeah. So hello world. It took this. It took that function. What is that function? Where do you call, bro? I just want to see like how many instructions are in between them. So where's main? Let me just jump to main and go down here. Okay. Set up the stack. Load. Okay, that's... You see, this is... I think this is the base page that we are requesting. And 96... Oh, by the way. Table. I think it's... What the heck? Character codes. Yeah, what is A? Could be 57 or something, huh? 65 or something. 60, 65. So, you have 65 here? Okay, yeah. So this is where it's writing to it. So it is the base page, right? You're requesting, this is for the function call for mmap. It's probably for the mmap function. You write the value 65 and then you're requesting this many for this size. And right after that is these are the parameters you're passing in. And this is, I think, the null, right? Because you're passing a 0. And whatever, this and that, you're setting it up. Then we go down here. And the timer, yeah, so like these are all like what? 15 instructions, like 20 cycles, whatever. Nothing happened, like, and then you time it. You memset. Initialize. This, that, RDTSC. Yeah, this is like basically opened up version of that Google timer start thing, and then timer stop, and then you just calculate the value, and you probably just then return it. Yeah. So yeah, pretty straightforward. You could see like maybe what, less than 1,000 cycles pass to do this, to do all of this, and maybe more than 1,000 cycles actually. But so yeah, so since this initialization, the cache line is going to be in the cache is the bottom line. And here, once you access it again, obviously you're going to get the cache hit. So you're going to have like an L1 or at worst like L2 cache latency, which 28 makes a lot of sense. Now, I'm going to remove this guy. I'm going to leave it for the love of the game though. 38, gotta be around the same thing all the time. So now what happens if we evict it, right? Now if you evict it right after you initialize it, what you could realize is seal flush opt, you will have, if you pass in the base page, now what would happen is it will no longer be in the cache, and I think it's best to fence it so you make sure the memory related operation is completed. And you can see now the access latency jumps to like 150 when you evict that cache line. So you can no longer get that cache hit. So you see, on average, I was telling you, like about 200 is the access latency on this machine. And I typically work in VMs with this machine. So in general, everything's a little bit slower. So when I have these like tests running, DRAM latency is typically like above 200, not below. But it seems like I'm bare metal because right now I'm not running in a virtual machine. It's like 100, maybe 80 on average, 170. Which is cool. Anyway, you get the idea. Now you can see what I mean, whether the access latency is high or low. You can tell whether something is cached or not. Now we kind of have our guesses on how the prefetcher is really behaving. So now let's start the real stuff. I'm gonna try and access how long it takes if I access like 128 bytes, meaning if I, oh, by the way, this is cool to see. So if I evict the first, like the starting address, you're evicting the first 64 bytes starting at the address, whatever this thing is, right? So whatever this guy's 0x, like x address of base page is this, and you can just give it oops, why did I put it in this? What's wrong with me? So you can see what the address is, and the cool thing is if you do the seal flush opt, it works in 64 byte granularity because it's a cache operation. So if you evict this guy, right, and you still access a cache line after that address, you're still going to get a hit because it's still there. When you evict, you're evicting anything from BP until 63 bytes after, including 63rd byte after BP's start. So something like this would get a hit. It would get a miss because it's been evicted, but I believe 64 should be a hit, which is pretty damn cool. It's like a heart surgery on your computer. Now, we're going to try and see what's going to happen if we now try to access continuously, okay, so I'm pretty sure at O2 you get loop unrolling. So if I have like a static variable like this and be like, I'm gonna access with a 64-byte stride, or not with a stride. Oh, actually, since I am only requesting one page, I can't test anything. Oh, we need a function that could evict like a entire range worth of cache lines. So like if I want to evict an entire page, I need to like stride at 64 bytes until the ending of that page. So I'm gonna need to write up a quick helper function for that, and still flush up to where are you? Okay. I don't think we could really do inline for this. I want to just suggest and be like seal flush range, right? Or yeah, seal flush range. Actually, the previous one was better. And then const void p, and I'm gonna give it a const u32. Should we have them calculate? Or like how many? Yeah, I think it's best to just like have it calculate this itself when you use the function. So you would need to give n lines. So calculate how many cache lines are to be evicted, assuming 64 bytes per cache line. So we're just gonna simply have a for loop that does this in lines many times, and it's just gonna do seal flushed up, and it's gonna be the pointer plus I times n length, I times 64, right? So I think this should be fine. And I think this could be in line. Yeah. Anyway, I think the compiler is smart enough to do that itself. All right. Yeah, this looks good to me. How many number of lines? Yes, yes, yes. Yep, looks good. Yeah. I just was running a sample with n lines being given like 2. We're just doing some tests. Okay. Let's go back to this guy now. And we're gonna try and evict. So if we have this many bytes, right? So we just need a see this. So there's 64, right? So we could just evict the whole thing basically. Or should we just give it an address range? No, I think it's just better. Yeah. I guess we could then make another helper that uses this guy. Inline void seal flush range n lines. Yeah. So then we could just have another function seal flush page that takes void p and yeah, We could have a dedicated function that would just like flush a page. See, I'll flush up the page, by the way. And then here we could have just copy this guy and paste him. Be like for I. Okay, where is something like a 4K page, right? And we're probably gonna a 2 megabyte page, right? Okay, so since we have 2 megabytes to bytes, so 2 million whatever. Okay, so if we have this, can we have how many times we need to do this? 32,000, whatever this number is. And let's just copy this guy, paste it into our beautiful, beautiful, beautiful C program. And yeah. So that would be the case for 2 megabyte. And in case anybody is, that is 2 megabytes divided by 64 bytes. And this one will be 4 kilobyte divided by 64 bytes. And which would give us 4096 divided by 6. It was 32, was it? Or 64. 64, yeah. So you could see that if you have an address, and 64 times 64 would, you know, go at 64 bytes, right? And okay, now we have our helpers, and now we could just simply call this guy and be like clflush 4 kilobyte page, and we just give him BP, right? And over here we could just access anywhere within that, like a kilobyte in, and it should just ideally be high, 150, whatever. Yeah. So it is. Now the whole page is being evicted. That's very nice. Now where do we get our... Okay, so now let's allocate 2 pages so that we don't access out of bounds. Oh man, it's 11:50. Okay, what is going on here? Do we have any news? Because right now the war in Iran started, and it's a hot mess. Oh man. Yeah. Anyway. So what do we have here? Now we're trying to train this guy. Right, let's do like, you know, maybe 5 and see if it prefetches the next page. It ideally should not. So 512 times 2, and sorry, you guys gotta go, and 512 times 3 and 4, and you might be like, why don't you write a for loop? It was faster. Okay, so oh, now all 4. What am I doing? Oh, yeah, I mean the whole page is loaded, right? So, or is it? Okay, let's see. Okay, let's fence these, and now we could do timer start. Okay, so if we access these, right? So this would be, would it learn and be like, oh, it's gonna now access, like, let's do like hope that it's gonna learn. Okay, no, this is way too ugly. I'm just gonna write a for loop. What the heck is wrong with me? So sure. What was I doing? Why am I cheesing? Okay. And let's see if this guy would be a low access latency. Yes, it would be. At times it wouldn't be. It seems, oh, this is pretty cool actually. So you could see, okay, I'm not really caring about, because I'm about to start writing some code here. So I'm gonna be like the address. So you guys could see the page offset shifting here. And what is this guy? So it would be BP or whatever it is, right? I mean, the base page is the same, right? But you can see how the page offset shifts by 512 bytes, right? So 512 bytes to hex. So it would be added by x200, which is exactly what is happening here, right? So now, after this, hoping to have this guy prefetched. Now the question is bro prefetched? No. At times he is, which is pretty cool. Most of the times he is. What percentage of the times now? And now the question becomes, would it be more accurate if we do, like, would it more frequently be a low access latency if we do like more training rounds? Because we could do this like 7 times before accessing it, right? Because our limit would be 4096, so we could test it at the 4096th byte. So we could like do this guy, or even do, well, actually, yeah, we could do this guy, and then use 512 times 8 at that point. Would be the max we could do with this range. Huh. It seems the prefetcher is kind of dumb. That's what I feel. I don't know if I'm doing anything wrong. But I like bell pepper though. Ooh! My amazing mother texted me. Interesting. Anyway, I'm gonna go do a bathroom break, and I'm gonna come back. I'm gonna go drink some water and stuff. Alright, I'm back. I was actually thinking to myself, in the bathroom, am I stupid for doing this without AI, or is it actually kind of good? Because, sorry, I'm speaking with my mouth filled with food, but what if you want to talk and you got food in your mouth? You gotta talk with food in your mouth. So sometimes you really can't do anything about it. But anyway, yeah, I think it doesn't really matter. I really thought about it. Because, like, this type of fine, controlled ways of having, like, uncovering microarchitectural behaviors, you can't trust AI. I'm actually gonna have ChatGPT give a go at this after I'm done with TS. But, you know, is it gonna know it should, like, where it should have the proper memory fences, load fences, how to read the timer, stamp counter, or where's my water? Yo, like, I don't know, to warm up the timer? I don't think so. I'm gonna give it a try. After this. So yeah. Where did I leave this? Okay. Huh. Very interesting. It kind of looks like to me that line is like at times prefetched into the level 3 because 60 is the rate for level 3 cache. Actually, hold on. I just want it to be pinned to the same core every time. And you gotta also, you don't want the thing, you might get preempted and have another process run on that core, and then you get rescheduled on a different core, so your timing might get messed up. In those cases, you'll see like a stamp of like 1,000+ cycles though. Is there like a nice primer? Like, how do you pass the nice primer? Do you just do dash nice or something? Like nice, I think you just run it with like nice, nice. Am I looking stupid trying to like, I forgot how I could write, how to run with niceness, run process. I forgot how you could do this. Process with niceness, value, like something, and like, you know, anything. Oh man, I already need water. Nice. It's a tool of some sort, yeah. So you do like, oh, you do dash n and then that thing. Permission denied. Okay, so does it go after? Yeah, so dash n. What do you mean invalid option? It should not be nice. Re-nice? I didn't know that's a thing. Nice? Oh. Re-nice. Okay, let's see how bro runs this. Nice option command. Okay. Oh. What? Why would you pass dash n to past adjustments? What, can't you just do it from the start? Anyway. Why can't I? Anyway, the program's running nicely without nice. How ironic. What am I doing? This is why it was getting cooked. Sudo nice -n -19 or something. Yeah, that's how it could run. I wasn't seeing the... Okay, so this just gives a high priority to it in the C group it runs in, so it doesn't allow it gets prioritized over other user space processes in case there's anything running periodically, and it wouldn't be preempted by another thing. Why did this turn on? This looks good to me. It seems like the prefetcher is doing something. Now I'm more interested in how many lines it prefetches until, but already by the unstable nature of this thing, I could kind of tell it's like we're gonna like be able to see a couple lines in the future being prefetched, but then not see it happen after a rerun. So I don't think it's like a static. Your phone has been updated to iOS 26.3? When? I don't even know. Okay, thank you. So yeah, now let's do this until 7 and try to see if we could still get 8. That means we're trying to see if we get 2 prefetches into the future. It seems... Yes. It seems we do. Oh. Oh, you saw the 1,000? Hold on. Let me remove that. Yeah. It seems we do get 2 lines into the future. At times, and it seems like it's prefetched into the level 3 cache and not level 1 or 2. Although the first one looks like it gets... The first one right after, at times it gets prefetched into... L1, yeah. Oh man, I'm actually so stupid. Hold up. Yeah, it looks good to me. It looks terrible to me. Why is it not being prefetched now? What is wrong? Hold up. I'm not tweaking, right? Oh, wait. This is not included itself, right? That's another page. Would it be illegal if we even do this? Would we even get a page fault? I don't think we will. Interesting. Okay. We didn't get it to core dump. So we will. However, now try 2 pages. Let's see. Page size. So we're getting 2 pages. Based on the quick test we just did, it doesn't seem to me. But what do we? I didn't know we're testing 2 pages. Would we get a page fault now? Because this would go past the first page's boundary. Oh, hold up. This is 5 kilobytes in. What is bro talking about? Holy moly. What the hell is this? What am I seeing? Is it pre-fish now? Or is some weird stuff is happening? Very interesting. So you were telling me accessing like this. Imagine some engineer at Intel is looking at me, knowing what's actually going on under the hood, and just like this idiot wasting his time. Or AMD or something. Actually, what's the MSR value? We have the so this is for all of them, just one of them. F. Okay, so is this Intel Xeon Scalable SKS volume 0? No. I had the book. I don't know. Hardware prefettures. First generation. Let's actually just go. This is the first gen, I'm pretty sure. Oh, yup. Give it to me. Yes. Okay, hardware. Prefetcher. What's fetcher? Scalable memory. Prefetcher. Reference manual. This is stuff that GPT would be good for, actually. You gotta be here, though. Let's download this guy. I definitely downloaded this guy before. I remember I forgot it's rainy. Where's the... I think that guy I think this guy is right. Okay. Yeah, I don't know what this thing is. Anyway, I could give this a try on everything. Right? Why don't we just... Okay, right now, let's just save the state of... So... we could just write F, right? And... gives F. And I'm gonna run the program one last time. Every second we check PKP. Okay. Okay. Address of whatever this guy says, just comment out. Just watch this, let's see. C1 gotta be, so the F is being prefetched or no? I am confused, guys. You guys are absolutely but something is wrong. If it's E, that is true, okay. Anyway. It seems it sometimes prefetches and it sometimes doesn't. So it just looks to me the prefetcher is working, although it's not necessarily always right. It just... So now what happens if we just disable this in the middle of this? Would it always go up? Unless I just wrote... Oh, hold up. This should not be here. Actually, can we just do this? And by the way, this should be like so you're telling me it's already disabled? Because like this is basically what it was, right? And we were reading it. Why did I think F is 14 for all this time? What the hell is wrong with me? Oh my god. I gotta be tired. Yeah, so it was disabled, right? So how do you enable it? This guy. It turns out bits 9 and 19 is the right MSR bits for Pentium 4. That's not what I'm looking for. The disclosure of Intel. The heck happened to this website? Was it not any longer having the Intel families? Can I download? Just give me the whole file. Prefetcher. CPU ID. What are these addresses? For the field definition. Oh man. Just keep going. Oh. Okay, yeah. Request type field prefetcher R of core. BX7 address 186H.
There's some effort being made.
What the heck? Okay. Counts the number of R for requested. Okay. Not interested. Not interested. Not interested. Not interested. Not interested. No, not interested in the counters. Ooh, the symbol. Register address. Appreciate TS. 0. 24. Okay. A. How old is this, by the way? What page is this? Page 99. Or whatever this page is. 35 out of 106. There is no way this is 100 pages. It's like thousands of pages. Okay. Occurrence 39. 35, whatever. What year is TS? 2026. Okay. Oh. Intel, MSR, Skylake, prefetcher, Sable, John Calpin, community.intel.com. Is this 9 here? I drank the water. I gotta go pee again. Well, I'll be back in a second. Alright, so I also went to the bathroom. I also came back and I was like reading and I realized I didn't click record again. But anyway, yeah, it seems to me this where did the thing go? Yes, so the 0xa 4. What was the thing we were trying? A4 H. Go to Lebro index. No, 0H exists for a fact in this thingy. It just has to search. Okay, so now let's do 4H. Okay, nice. Now, yeah, wherever this guy found this, Goldmont. So what is this one? I think this is where we fall, actually. Sandy Bridge, 12th and 13th. 4th and 5th generation also. So the 0 means Okay. Now, what else? This guy. This guy. Oh. No, this one is. Okay, anyway, it seems to me that it's disabled, which makes sense, because at times I don't see this working. But the weird thing is, then why is it sometimes low, right? Oh no, let's try enabling it. So this thing is now pinned to sudo msr-01 right. I think we just write 0, right? Mm, 1A4 0. Now let's see what bro does. Okay, it seems it is now consistently low, but if we write F, it spikes. So the prefetcher wouldn't work. Now if we write 0, I don't see any spikes. Oh, never mind. Weird. I'm actually not sure if any of those could be a result of context switch, though. But it definitely looks like F has far more spikes than when it's 0. I think this is genuinely disabled, and the 0 case is when it's enabled, but it's just that at times whether the prefetcher cannot guess properly to bring in the right line, like when I set it to 0, 3, 4, 5, 6, 7, 8, 1 out of 8, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16. Okay. Right now it has like a 4% chance of jumping. Now, what about this? 1, 2, 4, 5. 1 out of 5. 1, 2, 3, 4. Okay, 1 out of 4. 1, 2. Okay, 2. Yeah. Yeah, okay. It seems this is definitely the prefetcher's MSR. Okay, I need to run some tests though. I'm genuinely not sure. I gotta do some tests and see how the we don't need this. We simply need this. Yeah, so we just need that. And now do I have hyperfine? Okay, hyperfine. How do you build TS? Okay, how do I install it though? Package manager. Oh, sweet. I actually forgot. I guess we could just do hyperfine and it's just telling me how long my program runs for, right? So now, can I have hyperfine custom output, like output of my program? Can hyperfine benchmark average of custom from programs instead of execution type? Okay, back to square one. Oh, page cache? Decimal numbers, this, that. Okay, export results. This is nice. Okay, cool. Now, but how can I do... No. Let's see. STD out or something, like, can you print the STD out on error? Okay, anyway, I have my own script for this. I'm tired of this. I'm gonna just cat scripts bench, pretty sure. And now just copy this guy. Okay. And now bench. Scripts bench. And I think I could just do bench dash n like 100 times or 1,000 times and PKP. No. Okay. So, okay, an average we get. Some of them are. Now, what do we get if it's actually enabled? So we get about 60, 70. About 45. It's definitely doing something. Like, this cannot be coincidental. 1,000. There's some bad jumps though. Very, very bad jumps. Like 2,000. No, 800. I cannot be tweaking over this. There's no way. It's gotta be lower. It's definitely lower. Yeah, it's definitely lower. Okay, let's do 10,000. Oh, 1,000 is a max? I have a max? That's stupid. Yeah, I should discard very, very large values. I don't want to do anything crazy. Like, I don't... Do I just discard it like a hard limit, like anything above 500? Because honestly, anything above like 550 is probably an outlier. It's gotta be a context switch. Like 600 definitely. Like maybe 600. So anything above 600 really throws values off. So I'm just gonna do a T2 minus T1. Goes over. Yeah, I think 550 would be good. Let's just do 600 just in case. What am I? Yeah, I think this should be fine. So this is for disabled, not for enable. 60 about 10. Okay. Where am I not seeing anything really? Oh, it seems like it's low-key the same. You know, sometimes answers hurt, but this low-key... I don't know what to say. I don't know why. I don't know why. That gotta be the right. I mean, I remember. Right, gotta be the. Why is it searching output? Where did the manual go? Oh, hold up. It's writing F. Okay. Might be another. Oh, this looks good. Hold up, this looks good. It might have been because I did not. This is looking good. This is gonna be 100 minimum. Yes. Now what if we do 0 though? Yes. Okay. It was the wrong chord. It was just being scheduled on different chords. It should be about like 40. All right, great. So the prefetcher is... Yes! Okay, so the prefetcher works. 0 to enable, F to disable. Works like a charm. This is actually pretty surprising. And it's funny how it's like runs about 4 times slower. The attempts, like the whole benchmark takes about like 3-4 times slower because every single iteration is like. So this is actually a good example of like maybe you don't think of 60 cycles to be that long, but actually I can just time it. Like you could kind of see. This is like a basic example. When you go from like 30 cycles to close to DRAM latency, within only 1,000 runs, that extra 60 cycle kind of catches up and like hunts you down. It's like how many seconds? 17. Now if you enable the prefetcher, it's like definitely got to be sub 9. Oh wait, it also got to calculate the average. That's going to take a majority of time. Never mind, I lied. But anyway, across how many cycles? Oh, because main part is the time it takes to actually set up the program and run the program. You know, schedule it, run it, terminate it, initialize it as a process, etc. I mean, the program, that part itself is barely any. It is barely any effect. So, forget all the yap I just said. Yeah. Okay. So this works now. What about next page prefetcher? I saw in the book, in the same PDF, there was a next page prefetcher MSR that could be enabled or disabled. So I don't know if. Also, I think we could now disable. We could just disable this now. Just T2 minus T1 and Yeah, it looks good. It looks good. But it's kind of weird how sometimes still you could see them. I don't know, maybe it disables only one of the prefetchers, not the. Maybe one of the prefetchers in one of the levels, not all of them. And that's why you end up getting like. This looks like L2 latency. It's 36. 30 is like L1. 28 is like L1. Anyway, I don't know. I don't know why sometimes it's still. But it looks like majority of the times you're getting a miss. Which makes sense. So now what about a 2, like a cross boundary when you have your, so, okay, I gotta do this, and I gotta flush both of these pages, and allocate 2 pages, and then warm up whatever this and that, yada yada yada. Nice, great job. No. Wait, why do I warm up here? Am I stupid? How am I warming up here? It should warm up here. That could be a cause to why some of the measurements are low-key wrong. Do we have high 100 something anymore? That could have been an issue with the timer warm-up. Should be about like a perfect 30 now. 31. I don't know. Anyway, the timer warm-up should be around here. No, over there. Let's do 8, right? So this should be the start, but yeah, let's do the start of the other page. The prefetcher is enabled, if I'm not mistaken. So the next page prefetcher is definitely not working. Okay. The same page prefetcher is definitely working. The next page prefetcher is definitely not working, even if we bring in the whole thing, right? Yeah. What about this? Because I think this one would go in the next page though. Yeah, so this is fine. But if we do this... Interesting. Yeah, I'm gonna look into the next page prefetchers. Next page prefetcher. Hello, dog. Wake up, man. Okay, so this is 184. What family though? Ultra? No. Oh wait, this is 184H 4. So it's the same, but this is the bit. So the 4th bit. Gotta be more. There's no way this is the only occurrence of the next page prefetcher. What? No, you're lying. No, you're lying. There's no way. Really? So they don't even have an next page prefetcher? For... what? Okay. Release or anything? What year? Ultra 7. Okay, whenever this date is. Okay, this is rather new. Ours is definitely not that. Intel Xeon Scalable SKX next page prefetcher. Okay, so I do have this test now ready to go on for next page prefetcher on AMD. It's kind of verified on Intel that there is no next page prefetcher enabled, at least by default. It seemed that the next line prefetcher was also disabled by default. I don't really remember ever toggling this. I remember I messed up a bunch of options in BIOS regarding the cache lines. I don't know if I turned off the prefetcher there. I remember there was an option for it. Might have been my fault. I'm pretty sure they would enable it by default. I mean, I don't see a reason they would disable it, right? They typically give you the option to disable it yourself, but these type of nasty optimizations are enabled by default. Anything for the gains. Yeah, I don't know. I'm gonna just try this on AMD now. It looks to me. Let's just try one more thing. Just instead of doing a base page, let's just try and huge page, and I'm gonna just do a huge page. Okay, page size, and this should be fine, right? And this would be huge page, and this would be so huge page, right? So now what we could try is see if the huge page would be prefetched if we do this. Oh, what is going on? Uh-oh. Oh. I might have not enabled huge pages on this machine right now. Oh my god, I can't type. But why is it not catching it though? MF huge page. Still running? Okay, sounds good to me. So the task set this to that. It's setting to 0 to enable it. Now we run this. And then it looks good to me. And I'm gonna try the 8. And I'm gonna try the 8th one. Now if you run this, we can get yeah, it doesn't work past 8. Yeah, it doesn't work past 4 kilobyte for huge pages either. Alright, I'm gonna commit this and just Intel SKS. I think this is first gen. Doesn't as expected. Okay, actually, let me just type down the name of it. MSR for prefetcher. Prefetcher. To enable, to disable, and what else? No next page prefetching. It seems. Whether huge page or not. We'll try AMD next. Sounds good to me. Let's push this guy up. Alright. I shall rent a Zen machine and then try it on AMD Zen 5 or something. Gotta read a little bit of their docs still. Oh no, I am hoping basically this exact same version, if I run it, I don't get a high number with 4K, and I get I get a high number with 4K when I'm trying to access past the 4K boundary, but I get a lower number when I'm trying to do it with a huge page. Basically, I'm just trying to verify Dr. Bandwidth's comment on Stack Overflow. Where did he go? Yeah, I just want to confirm this on that specific generation of AMD processor. After that, should be fine. So, yeah. All right.